All right, so welcome back. We're going to move ahead into chapter 16. Chapter 16 is pretty short. There's really only one new mechanism to learn, but there's a very important concept that we have to talk about, which is going to lead into chapter 17 and 18, I believe. I'll double check that real quick before I give you guys some wrong information. I believe it's 17 and 18. Yeah, so chapter 17 and 18. So 16, there's a concept we're going to talk about pi bonds and p orbitals, and that's going to explain a fair amount of what we're going to learn in 17 and 18, and then it's even going to come back in one of the other chapters where we talk about carbonyl groups and alpha-beta unsaturated ketones. So one new mechanism to learn in here, although the mechanism's not, you'll see what it is once we get there. But anyway, so the main idea out of chapter 16 is that we need to figure out how pi bonds start to talk with each other, is what it is. And so we've learned quite a bit already, especially in the first semester of organic, how to make an alkene and how we can react an alkene also, right? So we've learned about how p orbitals and pi bonds can be formed and overlapped, and we can form, or we can react those then. And we extended that on into alkynes, right, which are just basically, if we want to think about it, two double bonds, right? So we have one pi bond and another pi bond, and each one of those pi bonds in an alkyne just reacts like a single, like a diene twice, basically, is what it is. I hope that kind of made sense, right? Again, if you guys had me for organic 1, then you would have been familiar with that, but again, it's whoever you had for the first semester there, right? Okay, so who cares? Why am I talking about that? So what I want to say now is that we're going to take those ideas that you guys learned about alkenes and just say, what happens if we do it twice, okay? And so here's what I mean with this, right? So conjugated systems, that's kind of the name of the game. All right, so we've learned about alkenes, right? That's what we're talking about. There it is, Mr. Pi bond, right? Overlap of two p orbitals. We talked about cis and trans and E and Z and all the different reactivity that comes with that. So now, if we move on to having more than one pi bond present, okay, we start to incorporate some different reactivity into that, okay? So now we have an alkene, and now we have a diene, right? So di, two, ene, alkenes, right? So diene, triene, tetraene, polyene, right? So we can have multiple pi bonds, and if you take a look in the book, right, they give you guys some examples of this, on page 741, there's retinol and vitamin A, and they talk about how that works when light gets absorbed into the eyes, and it changes the E into Z, or the cis and the trans isomers, and all this kind of stuff. Interesting, right? And so, again, not relevant necessarily to what we want to do in here, but especially for you guys who are moving on into any of the biochemistry work, right? It'd be kind of useful to look at that because conjugated systems are present in a lot of biological systems, right? Anyway, okay, so what we need to talk about and what the main concept that's coming out of chapter 16 is we got to talk about how those dienes or trienes or polyenes kind of talk with each other is what it is, okay? So a little bit of definitions first, okay? We can have a couple different examples of dienes. Let me just add this here all together, and then, that way we can make a quick comparison, right? So if we have these two systems here, they are both dienes, they both have 5 carbons, they both have 2 pi bonds. The difference being, right? The difference being where the pi bonds are, okay? So here we have pi bond, sigma, or I should be careful with this. We have double bond, single bond, double bond, okay? So double bond, then a single bond, then a double bond, right? Here we have double bond, single, single, double, okay? So the difference here, right, is this would be a conjugated system. The double bonds are next door to each other, okay? what we have over here, this is what's known as an isolated. Okay, it's still a diene, but it's an isolated set of dienes. Now, isolated dienes is what you guys have learned about all along, okay? These are going to essentially react the same way as just a single alkene will. Now, of course, there's differences, right? You know, we have allylic positions that are different here than they would be in, you know, some other systems. So we have to be careful. There is some, you know, differences with that, although overall, the isolated systems will just behave like we expect them to. The conjugated systems are going to behave differently, okay? So the idea is this, right? Let me paint the broad picture here and just give you guys the, you know, the bird's eye view. Whenever you can form a conjugated system, that's going to be a stabilizing effect. That's something that the molecules want to do, okay? Because as soon as we can put one pi bond next door to another, okay? And what I mean by next door is this, right? Double, single, double, right? So double, single, double, right? As soon as we can continue that pattern, it starts to stabilize the overall system, right? And you're like, yes, I believe everything that you say. Good, okay? But maybe not. Go take a look at what it talks about in the book. It has some fantastic pictures about some of the stuff that I'm about to introduce to you guys, okay? I'm no artist, as you guys probably have told or have figured out if you've stuck with me for this long. And so there's some fantastic computer-generated images that are in there that kind of explain a lot of these concepts that are there, okay? But formation of conjugated systems is a electronically driven effect, right? And what I mean is this, right? If we can form a conjugated system, then we will want to do that, right? There is a drive to do this, okay? And the reason is because what would be the simplest way of saying this? The picture that we draw, right? The Lewis structures that we draw here is not the complete picture of how orbitals are interacting with each other, okay? And so that goes back to general chemistry where we talk about molecular orbital theory, okay? And you might have even touched on this in the first semester of organic chemistry, right? So what I'm starting to talk to you guys about is, let's see here, this is kind of going through the pictures and stuff that are on in section 16.3, right? So if you guys are following along in the book, I'm looking at section 16.3, and they talk about molecular orbital diagrams and pi bonds and, bonding orbitals and anti-bonding orbitals and non-bonding orbitals and all that kind of stuff, okay? So take a look at that, and you guys can see some very nice pictures with this. At the end of the day, the more bonding orbitals we can make, the more bonding interactions we can make, the better, the more energetically favored that is. So let's deconstruct this for just a bit. Let's simplify this right here and kind of talk about what we mean, okay? So how do we make a pi bond? Okay, so let's say there's Mr. Carbon atom there, and there's Mr. Carbon atom right there, okay? If we want to make a pi bond, remember a pi bond has electron density that's above and below the plane of the atoms, okay? So a sigma bond is in between the two atoms, a pi bond is above and below, right? And, you know, above and below is relative, right? Above and below or in front and in back, right? So those are the two, those are essentially the same here, okay? So there's a pi bond here, okay? Let's, I gotta be careful here. There's a pi bond there, and there's there's a p orbital there, and then there's the other p orbital there that's on these two carbon atoms, okay? So why is one red and one's blue? That's typically the colors that are assigned for the different phases of the function, okay? So remember, let me stop here for just a second, right? When I'm drawing pictures of orbitals for you guys, really what I'm doing is I am acting like a TI calculator, okay? We input a function and we get a picture, right, based off of that function, right? So if you guys had your graphing calculators and you input, you know, some kind of function into that, right? If we had the correct function, we could get the visual representation of those orbitals, right? So this is just math, right? Okay, so this is just math. This is a function that shows a p orbital, and this is a function that shows a p orbital. If you add two functions together, right, they just make a new function, right? Okay, so that's how bonds get formed, at least from the mathematical perspective. Am I simplifying that? Yes, I am, okay? But that's not the point here, right? All I'm saying is we can mix orbitals together, and that new orbital that gets made is a combination of the two orbitals that you put into it, okay? So that takes on characteristics of all the orbitals that you put in. Garbage in, garbage out. What you put in is what you get out, all right? So conservation of energy says that if I put two orbitals in, I better get two orbitals out, and all this kind of stuff that's sitting there behind the scenes. If I'm talking really fast and you're missing all this stuff, it's because, right, technically this should have been done in Gen Chem, right? And if you're like, oh my gosh, Gen Chem was years ago, or Gen Chem was weeks ago, or Gen Chem was, last week, I forgot it already, right? Well, pause it here for a second and just, type in molecular orbital organic chemistry into, YouTube or Google, and, I'm sure there's some great, short little videos that are there also for that, okay? So if you're missing everything I'm saying here, it's because I'm, the underlying principle of MO theory is not what we need to talk about necessarily. It's just I'm trying to, knock the rust off here to kind of remember where we all came from, so to speak, right? Okay, hopefully that made sense. So if I'm trying to make a pi bond, I bring two p orbitals together, right? So physically, I'm moving these carbons together in a manner so that they can finally overlap with each other, okay? So that the orbitals can overlap in some way, right? By bringing them closer together, the functions can overlap, and we can make a pi bond, okay? Cool. With me? So I bring these two together, squish them together, and then I make a pi bond. Remember, the electron density is above and below the plane of the atoms themselves, okay? Now I can just extend this off into infinite, okay? So if I have multiple carbon atoms, let's just say that, there are my green carbon atoms right there. Each one of those has an unhybridized p orbital, okay? So I just have, right? So I just have this set of p orbitals here, right? And if I bring all those together, okay? If I bring all those together in this combination, what I will end up doing, right? I just got to make a subtle change here, right? If I bring all four of those together, now all four of those orbitals end up talking to each other, okay? So all four of those orbitals end up talking to each other, and this is why it's important that we have a distinction between the isolated and the conjugated systems, okay? If one of these carbons didn't have an open p orbital, then I couldn't have all four of these talking together. Now, some of you guys, if you're observant, you say, hey, wait a minute, right? How come this is showing one pi bond, right? But over here I've got two of them, aha, right? So there's a lot more that goes into this, okay? So this is what I was talking about, where we kind of have an incomplete picture if we just look at Lewis structures. It's not wrong, okay? It's not a wrong picture, it's just depending on what level you want to get to, okay? So remember, every time we draw a Lewis structure, we're shorthanding a lot of math, okay? And if we want to kind of dig into that math, right, then we can start to see where, our model that we draw here, right, our model falls apart, okay? So there's the saying, and I think it's even more relevant these days given what happened with, let's say the virus modeling, right? Every model is wrong, right? Just some are more useful than others, okay? Right? So Lewis structures, I'm not saying that they're wrong, I'm just saying depending on what question we're asking, they might be wrong, okay? And if we're really trying to explain why conjugated systems have to be set up in this way and how they behave and how they react and all this kind of stuff, we need to take a look at MO theory, right? And that's where I'm asking us to take a look at the pictures in the book there, right? I physically can't draw all these because I stink at drawing, and they're already drawn in the book. I don't need to copy that stuff back out for you guys, okay? Remember, my purpose here is to kind of digest the stuff in the book and give it back to you, okay? So what we end up with when we mix all these is a bonding combination, okay? And then as we start to increase our energy of our system, as we start to walk up, we start to change the energy, or excuse me, start to change the arrangement of the orbitals, where we start to create bonding and anti-bonding orbitals and bonding and anti-bonding combinations, all right? Now, the point being this, right? So I just wanted to simplify this into one picture. Obviously, there's more into that, right? But what I'm saying is that all four of these atoms here are talking to each other, okay? And so because of the overlap of the orbitals, because of the way those orbitals are arranged, and because of their physical locations in terms of carbons that are next door to each other, that's how we start to see some of this reactivity and special properties that come from these conjugated systems, okay? All right, for all of you guys who kind of zoned out and you're like, he lost me when he started talking about math, come on back in, right? Let's see if we can simplify this back to something else that's not mathematical based there, okay? All right, so how can we make these conjugated systems, right? How can we deal with them? Well, here's what it is, right? So if I ask you, let's do a little bit of review as we're kind of walking through here, right? There's our symbol alkene. You guys should be able to name that at this point, right? It'll be kind of good practice just to kind of keep this in your mind here, right? Now, if I want to, okay, if I want to add a bromine there, right? Do you guys remember the conditions to do this, right? You can do this in a single step, and it's actually a very important reaction to kind of keep in mind, okay? Now, let's pause here for just a second and take a look at that green carbon. That green carbon is particularly special, right? That is an allylic. That is an allylic carbon. That is a carbon that's next door to a pi bond. Why is that particular carbon so special? Well, this kind of goes into this idea that we just have with conjugated systems, okay? So let's say, right, just for argument's sake, that we end up generating this intermediate as we go through the mechanism to get to here. You don't, but that's okay, right? But let's just say we end up generating this right here. Now let's back up for just a second, okay? And let's switch colors to purple, okay? So we have purple carbon right there, okay? Now let's bring in the idea that we were just talking about with conjugated systems there and how how individual atoms can talk to each other. So carbon, okay? If we go back and think about it, what's the hybridization for all three of these purple carbons there? Well, the hybridization is sp2 for each one of those, right? And if I'm sp2 hybridized, that means I used my 1s orbital. I used my 1s orbital that's available, okay? Not my 1s orbital, it's the 2s orbital, but it's the 1s orbital that's available, right? I hope that made sense. I used my 2s orbital, there it is, okay, that might be a little bit more clear, okay? So I used my s orbital that's available, and I used 2 of my p orbitals that are available, okay? Which means I have 1 unhybridized p orbital that's left over, right? And so if all 3 of these have unhybridized orbitals, okay, and they're all p orbitals, okay, that means that all 3 of these carbon atoms right here can talk with each other. These orbitals are going to overlap. And that's important, okay? That's important because what we could say here is similar to what we just saw up there, right? All 3 of these orbitals are next to each other. They're of the same shape, right? They're all p orbitals. That means all 3 of these can talk to each other. Because, right, what are you guys familiar with doing? Well, you guys are familiar with drawing resonance structures, right? So, what is a resonance structure? Well, a resonance structure would look like that, right? Have you guys ever stopped to think about why we can form resonance structures? Because what it says is that all 3 of these orbitals, let me put the colors back in there, right? This isn't unusual, right? We have a positive charge next to there, we got to spread it out, positive charge. Now, obviously, one of these is going to be a preferred resonance structure over the other because they're not identical, but have you guys ever stopped to think about why we can draw resonance structures and why can I only put the positive charge on these 2 ends right there? Why can't I put the positive charge in the middle? And it has to deal with how these orbitals line up with each other, okay? And so there's a fantastic set of information that can come out of understanding molecular orbital theory, right? And when you guys go on to physical chemistry, and I don't know if FGCU offers a computational chemistry or not. I'm sure they do, right? You guys will talk about this exhaustively in there, and it's very, 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 very useful information, especially for you guys who are interested in the research, right? Lots of useful information comes out of MO theory and helps us to explain why the positive charges end up where they do, okay? But the point being this carbon right here, right? and this carbon right here, these are the allylic positions, right? They are next door, right, to a double bond, and those are particularly reactive in terms of stabilizing a carbocation or a radical, right? Because we can draw resonance with them. And the reason why we can draw resonance is because we can overlap the orbitals of the atoms that are involved, okay? So that's the only part that I really want to tell you about. Now we're going to come back to this concept in maybe about 2 lectures or so, when we're going to talk about aromatic systems and what defines an aromatic system. But it all has to come down to this idea of overlapping orbitals. Those orbitals have to be next door to each other. That's it, okay? So if you just zoned out for the last, I don't even know how long I've been yammering now, right? That's the only idea. We have to have orbitals that are next door to each other, that are available, that can talk to each other, that can overlap. Done, okay? Anyway, right? So to go back here and answer the question, right? This is, go take a look at NBS or N-bromosuccinimide, right? That is our go-to choice there for adding an allylic bromine, okay? And usually we have to put some energy with this, some H nu, right? Some type of heat or light or whatever it might be, and then we end up adding a bromine to an allylic position there, okay? Now, the mechanism is radical. There's a radical mechanism involved with this, so this might be a good point to kind of stop and knock the rust off of radical mechanisms if you guys don't remember those, okay? But anyway, let's say we do this reaction, we make that, okay? And then we come in and we will use one of our favorite reagents here, okay? All right, so what do we have? Okay, so here we have our buddy T-butoxide, right? Tert-butyl oxide, okay? Now, there's something important to recognize here every time I give you guys something, right? I know I tend to mention this in pretty much every lecture. Stop, think, look, analyze, what do I have, right? So we have an oxygen with a lone pair and a negative charge. Attached to it, it's got a bunch of junk, right? So it's carrying a lot of emotional baggage with it, right? It's sterically hindered is all I'm really trying to say with that. So we got a sterically hindered negative charge. Here we've got a good leaving group at a secondary carbon that is allylic to a pi bond. It's at a allylic carbon, which means it's next door to a pi bond. Okay, do you guys catch all that? So good base, that's sterically hindered, strong base. How do we know that it's a strong base, okay? So then we have a good leaving group that's allylic because it's next door to a pi bond, right? So all this is ticking the boxes to say that we are going to do an elimination, okay? So if I do an elimination, remember, I have to look next door to find a hydrogen that's available, okay? So here we've got hydrogens available on that methyl group that's on the end, and we do an E2, right? Our concerted elimination mechanism to generate our product. And so what would our product be in this case? Well, our product would be that, right? We will come and grab off one of the hydrogens here, right? And we will E2 to make that right there. What did we end up making? Well, we ended up making a conjugated system, okay? That's not just because I'm trying to stack the deck, right? Anytime we can make a conjugated system, right, that'll be kind of that will tend to be the dominant product that gets formed, okay? Now, we knew that we had to do an elimination anyway because we wanted to get another bond in there, so we're thinking back to E2 and E1 type mechanisms in SAPs, right? But for this to happen, we will have to use E2 and we will have to use a bulky base, okay? We'll have to use E2 and we'll have to use a bulky base. The book talks about T-butoxide, that's kind of its go-to choice. There are other bulky bases that can be used with this also. If you take a look online, they give you some examples of that. If you look up formation of conjugated systems, LDA is probably a very common one, lithium diisopropyl amide. And we will come back and talk about LDA when we have some different reactions that we want to come to, right? So anyway, right, not to introduce too much at once. So looking for a bulky base, an allylic leaving group here, and if we put those two together, then we'll tend to make a conjugated system, okay? Wonderful, now we know how to do that. All right, so what else do we need to figure out at this point? Well, once we have a conjugated system, right? Once we have a conjugated system, let me go to my notes here, what I want to chat with you guys about. So what, right, is the first question, right? So what? Well, now that we have this one we just made, okay? Let's bring back a little review here then, okay? So let's start down here at the bottom, right? If we have just a simple alkene and we react that with some kind of strong acid like HBr, some kind of halo, halogen and bromine, right? So we have hydrohalogenation, right? So hydrohalogenation, we're going to add an H, we're going to add a Br. Can you guys go through the mechanism? Do you guys remember how to do this? Can you guys get the correct? Can you guys get the correct products for this? Okay. And so, sure I can, right? Pi bond reaches in, right? We make a bond, we break a bond, we end up generating a carbocation right there. Fantastic. Behold its magnificence and its annoyance, right? And then, right, we do the ever important thing. Every time we generate a carbocation, we stop, we think, say, can I rearrange? Can I shift? Can I do any of this kind of stuff? Right? It's at a secondary position, right? Next door there's a secondary, over here there's a primary. Not going to do any shifting for us in this case, okay? And then we end up adding the bromine to the most stable position for the carbocation, which means, right, that would be my product. And if you got that, cool, all right? Except you're not 100% correct. What did you miss? Oh no, right? Something to think about, right? Remember, when you generate a carbocation, it's a planar, right? It's a planar intermediate, and the incoming nucleophile can attack from either end 50% of the time from the top, 50% of the time from the bottom. Which really means, if I want to be technically correct with this, right? I'll say I will make, what is this? So this would be R, right? Yep, so this would be R2-bromobutane, and I would make S2-bromobutane, right? So whenever you look in the book and you say this plus En, right, we're just talking about its enantiomer, right? The non-superposable mirror image, the R and the S, okay? So don't forget about R and S and all that kind of stuff also, okay? So don't forget about that. Whenever you have a carbocation, you tend to make a set of enantiomers unless there's some kind of other circumstances going on with that, okay? Great, so that was a good review. What happens if I try to do the same thing here? Okay, well, the answer is in the book, so you're like, well, I already read it. Okay, well, follow along with me then, and let's think through this. Okay, pi bond will act like a pi bond. Okay, it's going to reach out, grab that hydrogen. Anything different so far? Well, maybe, right? Maybe. Let me kind of bring this down here. Oh, that was weird. How do I undo that? Well, I'll just delete that for now. Delete. Oh, I see what I did. Okay. Anyway, sorry about that. Okay. So what's different about this and this? Well, carbocation, 4 carbons. Okay. Allylic. Right. So this is an allylic position. So we do have to pay attention to that, because every time we have allylic, we should say, hey, can I do a resonance structure to make a more stable carbocation or anything like that, right? And that's going to be the distinction here, okay? So the distinction here is, will that resonance structure happen, okay? Will that resonance structure happen? Here's what I mean, okay? So let me move this out of the way, just to give myself some space. And I'm going to do the exact same thing that we just had there, right? But I'm going to use a different color. You guys will see why in just a second. All right. Now let me come in and make a distinction here. I'll use the numbers in the book, right? We'll say this is at 40 degrees Celsius, and that's at 0 degrees Celsius, okay? Essentially, all I'm saying is hot and cold. Right, we warm it up a bit, or we keep it as cold as we can. Okay, so here's what happens then. Okay, all right. You guys with me? Oh no, I ran out of room. Move this over here real quick. All right, cool. You guys with me? Right? Add the acid, carbocation, do resonance, and we add the bromine here. Now, let's give this a name. I should have done this beforehand, but let me put some numbers on there, and I'm just going to walk around here because I got to make sure that that color shows up. That looks pretty good. Okay, so right, I've got 1, 2, 3, 1, 2, 3, 4 over here. Okay, so what we have here is 1, right, 2, 3, and 4. So I will call this a 1,4 addition, right, a 1,4 addition. All right. Let's follow along in the green. I know what you guys are thinking. I know. I can hear you. Don't worry. I will answer the questions. Okay. I will give this a name. I will call it the 1, 2 addition. All right. We'll pause here for a second if you guys want to pause and copy stuff down and whatever you guys need to do at this point, okay? So, what is different, real quick, right? What is different between here and here? The answer is essentially nothing, right? You add the acid, you add the bromine, and right? You make the intermediate, you add the bromine, you get to your product. Obviously, we could have the same argument here, right? About enantiomers getting formed. What is different here? We have an extra step where we have to go through resonance, right, to get to that one there. All right, so what does this tell us, okay? Well, there's one other term that we kind of have to throw around here, right? We have kinetic, and we have thermodynamic, okay? All right, so kinetic and thermodynamic control, or kinetic and thermodynamic product, okay? Now, let's define something real quick, or let's define it in 30 seconds, so to speak. When we're talking about kinetics, we're just talking about how fast something happens, okay? Right? You guys talked about kinetics quite a bit in general chemistry, right? We talked about rate laws and all that kind of stuff that's in there, right? Thermodynamic, this is just kind of referring to the energy of a system, okay? It's just a particular measure of the energy of the system, right? There's multiple things we could talk about, right? Enthalpy and free energy and entropy and all these different measurements of energy that come along with that. How fast something happens, how stable something might be, okay? That is the, if you're on the street and somebody asks you to explain kinetics versus thermodynamics in 5 words, right? How fast, how stable. And I did it in 4, never mind. Okay, so you guys get the point, all right? Does that make sense though? Well, let's think about this, okay? So how many steps does it take to get here? Well, we have 1 step, 2 steps. Okay, how many steps does it take to get here? 1, 2, 3. So it'd be like me asking you guys, do you want, okay, I will give everybody an A, but you have to run 2 miles or you have to run 3 miles. It doesn't matter if you pick 3 or 2, just if you do one of those, you'll get an A. Which one are you guys gonna pick? Well, you guys are gonna pick to run 2 miles, right? Because you get the same reward, so to speak, right? And of course, pick the simpler task, right? That's what we mean by kinetic, right? The faster way to get there is what it is, okay? Thermodynamic just means, okay, you're gonna take the extra step to, so to speak, you're gonna take the extra step to get to the more stable product, okay? Does that always mean the kinetic and thermodynamic products are different? No, it does not, right? Quite often, what we've been talking about so far, the kinetic and the thermodynamic tend to be the same ones, okay? And that's pretty common, right? But the difference here is from the temperature, okay? What does changing temperature affect? Well, essentially, temperature is just a measure of energy, okay? So if I gave you the same option here, right, say, okay, I will give you an A if you either decide to run 2 miles or 3 miles, and you chugged like 10 Red Bulls before you came to class, and well, assuming you hadn't died, right? So if you had a lot of excess energy, right, you would go ahead and run that extra mile, right, just to burn that off, okay? And that's all we're talking about. We are just adding more energy to the system so it can take that extra step and get to the more stable product there at the end. That's all we're really talking about with kinetic versus thermodynamic, okay? So hopefully that kind of made sense. Now, what does that practically mean for you guys? Make sure you're paying attention to the temperature when you're doing additions to conjugate systems, okay? When you're doing addition to any conjugate system, we have to pay attention to 1, 2 versus, additions that involve the resonance structures. Here's what I mean with this. Why did I call this a 1,2 versus a 1,4? Well, we had 4 or 2 atoms involved, right? If I had a triene, then I would have to look at 1,2s versus 1,6 additions, okay? Where we have resonance structures in between there, right? So pay attention to the temperature and what you're doing with this. Does this work for all addition reactions to a conjugated system? In short, I'll say yes, okay? In the book, they just give you guys some specific examples, and I think those are perfect to look at, right? They're pretty much all we really need to talk about for the moment with this, okay? So hopefully this all made sense. I think this is a good kind of break point for this chapter at least. The next video, we'll talk about the Diels-Alder reaction, and then we'll very quickly move on into chapter 17 from there. All right, I will see you guys next time.